number, if we look at the constraints over here, find the minimal k such that k is equal to m factorial. So we'll talk about that in just a sec. And then also k is greater than or equal to n, the input we're given over here. Okay, so basically we want to find the smallest factorial, which is not less than n. Okay, so what's factorial? We should probably start by talking about that. So, oh, whoops, guess I forgot to clear that. Let's clear it now. Okay, so factorial is basically, it's a math operation, right? So if we wanted to do 5 factorial, you might have seen this before. It's kind of like our most enthusiastic math operator here, 5. Basically what it means is we're going to take this number and we're going to multiply it by all the whole numbers, or all the natural numbers smaller than this is what I should say. So it's basically going to be 5 times 4 times 3 times 2, and then technically like times 1, but we don't really need to include the times 1 because it's not going to change the value. I'll put it in there just for the sake of completeness. But the main thing is that what we're going to get from this is not going to change by putting the 1 on the end of it. That's the idea. Okay, so what do we get from this? Well, 2 times 3 is going to be 6, times 4 is going to be 24, times 5 is going to be 120. There we go. Yeah, Rainbow, you learned about in 7th grade? Yeah, I saw it fairly early on as well, but like back in the day when I was a math teacher, I found that a lot of students were not really familiar with this. So I figured it's like probably worth it to talk about it. Anyway, if anyone has any questions, let me know, but that's basically what factorial is all about. So basically the way I want to go about doing this problem is I'm going to write a function to begin with that's going to give us just the factorial. Okay, so, and maybe that'll take an input. That's probably a good idea. So it's going to take in num, and it's just going to give us the factorial of num, whatever it is. So we could do this in a couple different ways. I mean, one way we could do it is to use a loop. We could just say something like, let fact be assigned the value of 1, and then something like this. We could say for let multiple, should we call it multiple? I don't know. I guess it's more like a factor. So factor, geez, this is getting pretty, like we've got 3 variable names that are very close to each other right now. So the autocomplete is not going to be very nice, but oh well. Let factor be assigned the value of num while factor is greater than 1, I guess we could say. Factor minus minus, and what we basically want to be doing here is saying fact is going to get multiplied by factor. Okay, and then at the end here we want to return fact. So let's see, is this working? Let's just check this function factorial. There we go, factorial of 5, we should get 120, and we're getting 120. Okay, so that's good. That works. That's a way of doing it. Is there another way of doing it, a better way of doing it? Well, I don't know if it's better, but another option we would have would be to do this recursively, right? So we've sort of seen that before. Instead of doing it this way, we'd do something like if our num is greater than 1, then we're going to return num multiplied by factorial of num minus 1. And then, oh, don't want to forget the semicolon, geez. Else, we just want to return 1. If num is not greater than 1, we'll just return 1. Okay, so that's, I think, another way of doing it. I think that'll work just as well as what we have before. Hey, what happened to my call here? I guess I cleared it. All right, so we should get 120 again from this. Oh, but we're not. So let's investigate. Why is this happening? So we're taking our num here. If num is greater than 1, we want to return num, so in this case 5 times factorial at 4. Okay, and then factorial at 4 would say, is num greater than 1? Yeah, it is, so return 4 times factorial. Why is this not working then? Last return, oh yeah, oh my god. Here I am trying to debug the function, but yeah, forgot the return. Thanks, Rainbow. Appreciate it, man. Okay, so 120, that's good. It's what we're looking for. Whew. Close call there. Okay, so that's another way of doing it. But of course, like, check it out. We're doing a return here. We're doing a return here. We could use a ternary operator and just say return num is greater than 1. And if it is, then we'll return num times factorial of num minus 1. Otherwise, we'll return 1. And that's, I think that's a lot more efficient. That's nice. If it's working anyway. Hopefully it is. Let's find out. Ooh, syntax error. So why would that be? Is it... Okay, num is greater than 1, question mark. Yeah, so it's going to return this, or it's going to return 1. Well, geez. Isn't this the same as what we had before? What's the problem here? Why are we getting the syntax error? I'm assuming it's returning, like an empty over here. Okay, well, let me take a step back. So it was okay like this, right? Yeah, it was okay like that. So return num is greater than 1, question mark. Well, did I forget the return again before? I'm not sure. Let's find out. Yeah, return num is greater than 1, question mark, either this or this. Yeah, that should work, right? Is that what I had before or no? Oh, okay, I guess it wasn't what I had before. Was I missing the return again? Was that the idea? I'm not sure. Anyway, okay, we've got this now. This is working. It's using a ternary. It's a recursive function. It's pretty nice. It's a lot of fun. Okay, so then basically what I'm going to do here is I'm going to go through our possible factorial numbers, or how should we do this? Basically, what we want to do is we want to find a number that's going to be greater than, we want to find a factorial that's going to be greater than or equal to n. So I guess let's make an m value, like what they have over here, right? Because they're saying m is the number that we were multiplying by in order to get this factorial. We're taking the factorial of m, and that's what k is going to be. So we could do something like this. For let m be assigned the value of 1, and I'm just going to leave the middle blank for now, and then m plus plus. And basically what we want to check is if the factorial of m is greater than or equal to n, then we're going to return the factorial of m. And that's it, I guess. I mean, I was going to put like a return statement at the end or something like that, but we don't really need to, because basically the idea is that this is going to continue until it finds a factorial that's greater than or equal to n. Now, technically, okay, first of all, let's just run this. We'll see if it works. It works. Okay, so that's great. But technically, there's something that's bugging me about this, and it's the fact that we're doing this factorial of m twice. So instead, let's just assign a constant of k, because that's what k is, right? It's m factorial. And we'll say if k is greater than or equal to n, that's what we're looking for, right? Then return k, because that must be the k value we want. Okay, great. So let's just make sure that passes all hiddens. Ooh, and it does. And this is nice, right? Making 300 bucks again off of one of these challenges instead of like the 100s we were getting before. That's nice. It feels good. I feel good about that. Okay, cool. So that's working, right? It's giving us what we're looking for. It passed all the hidden tests. It's not like it's timing out or anything like that. So that's one way to do it. But I want to look at a slightly different way of doing it. And here's what we'll do. We'll take a look at this other method. We'll talk, I guess, a little bit about the efficiency of it, but we're going to mainly save it till the end. Like at the end, we're going to look at all of our different strategies we came up with. We're going to compare them in terms of efficiency. We're going to talk about their advantages and disadvantages. And we're basically going to do a skeleton outline of the larger activity that we're going to end up doing for like task 30 or 31 or something like that. Okay, but for now, I guess I'll just clear all this. The issue I have with this is basically that we're saying, okay, we'll start m as 1, and then we'll calculate its factorial. And if that's not big enough, then we'll move m up, right? We'll make it 2, then we'll take 2 factorial, right? We'll execute this function again. If that's not big enough, we'll increment it again, so it's 3, then we'll do 3 factorial. So the issue that I have with that is basically what we're doing is we're saying, okay, I want 1 factorial. What's that going to be? Well, it's just 1. Then I want 2 factorial. What's that going to be? It's going to be 2 times 1. Okay, now I want 3 factorial. What's that going to be? 3 times 2 times 1. Okay, now I want 4 factorial. What's that going to be? 4 times 3 times 2 times 1 is the idea. Okay, but here's the thing. Like, why bother doing all of this? And especially because it's a recursive function, right? So this is going to put more onto the call stack, right? So why bother doing all this if we already know this? Like, we already calculated 3 times 2 times 1 in the previous step. So there's not really much sense in going through all of these calls when we already know what this number is going to be. So one way to do this would be to use a strategy we've seen before called Memoization, which would be basically where we build up an array of values, and instead of asking is num greater than 1, what we would ask is num one of the indices of our memoized results, our array of memoized results. And if it's in there, it'll just return what's in there. So that would be a way we could handle it, but that's honestly kind of overkill for this problem, because we could handle this pretty directly. We could say from the get-go, let k be assigned the value of 1, and we could say something like let m be assigned the value of 1, m for multiplier, I guess. And then, okay, how are we going to do this? We'd do something like maybe I should have done this. Let m be assigned the value of 2. No, let's make m be assigned the value of 1, and we'll leave the middle blank again. We'll do an m++. And basically now we'll say k times equals m. And I realize I don't need to have this here. In fact, it would be a problem if we had that there, because we've already done a let on that. It would probably have an issue. Okay, so we'll say k times equals m. So k is 1 to begin with. First, we're just going to multiply it by 1. No big surprise there. And then we're going to say if k is greater than or equal to n, return k. Whoops, not l. Return k. So is that enough? Is that all we need here? Yeah, that's all we need here. So that's a little nicer, because basically we're not recalculating k every time. We're not coming up with a brand new k value. That's the result of this factorial over here. Instead, we're just starting k as 1 and just multiplying by the next highest number sort of thing. So over here, if we want to take a look at how this is going to progress, well, we're basically going to say 1 factorial. Okay, well, that's just 1. We already have the 1. 2 factorial, oh, well, that's just going to be 2 times whatever we had before. 3 factorial, it's just 3 times whatever we had before. 4 factorial is just 4 times whatever we had before. So we're just multiplying once by our m value. So that's a little nicer. I mean, in terms of efficiency, we're doing a little less in terms of repeated calculations. Everything we see in the red here, these are calculations we would have to do over again in this version, whereas we would not have to in this version. Now, that's not going to make a huge difference in this particular problem, especially because if you look at n, it's only going up to 120. That's like nothing, right? So basically, the idea here is that it's not going to make a huge difference. In fact, it's not even going to make like a perceivable difference for these kinds of numbers. But if you think about it, if n could be something much, much larger, like if this loop was actually going on like 100 times, then that would end up being a lot of calculations. So it's significant. Okay. I do want to address one other thing, which is basically that we said it only goes up to 120 here, right? So another way we could handle this is we could take that into account. So I'm going to say const factorials is assigned the value of basically just all of our factorial values that we could possibly have in this problem. So we could have 1 factorial is 1, 2 factorial is going to be 2, multiply that by 3, we're going to get 6, multiply that by 4, we get 24, multiply that by 5, we get 120. Look, we're already at 120. These are the only ones we really need to keep in mind here. And then basically from there, we could just say something like, I don't know, do a little for loop for let I be assigned the value of 0. Or hey, better yet, for const factorial of factorials. Okay, something like this. So we'll use a for of loop. And we'll just say if factorial, whoops, extra space there. If factorial is greater than or equal to n, then just return factorial. So does that work? Yeah, it works. Okay, so this is not bad, right? I mean, it's getting right to the point here. We could probably make this a little more efficient. I mean, okay, there's one. Have we talked about this before? This dot find over here. is something we can use in this case. So the way .find works is just, it's an array built in, just like .map, .reduce, all those fun ones we like to use. So naturally, it's going to take in a function as its argument, and that function is basically just going to be executed on every single one of the elements, just like a map or a reduce, or more like a map, I should say. And then basically, it's going to take in that element, so like 12, it's going to put that in for element, and it's going to return sort of like a true or false on this thing. As soon as it returns true, it's just going to return the number that made it true. So whatever the element was that made this thing true, that's what we're going to get from the .find. So basically, in this case, we're looking for an element that's greater than or equal to 15. So we'll go through the .find, we'll say, well, is 12 greater than or equal to 15? False. Is 5 greater than or equal to 15? False. Is 8 greater than or equal to 15? False. Is 130 greater than or equal to 15? Yeah, I think so. So we're going to return the 130. That's basically the idea. So we can use the same sort of strategy over here, and instead of saying like constant factorials, we could just say return. Actually, hold on a sec. Let me just one step at a time. So instead of this loop, I should say, we'll do return factorials dot find, and then we want an element. So I'll call it k, right? Because that's what we're looking for. K is greater than or equal to n. Okay, could we just use this? Yeah, we could. So that's maybe a little more efficient. And I mean, this is what factorials is. So we're only using it once. We don't really need to give it a name in this case. So would that work? Yeah, it turns out that would work. Okay, cool. So on multiple true returns first. Yes, I believe that's the case. Yeah, it's what we're seeing here, right? So I think this is the evidence that that's the case, right? So you're saying like if there was, well, yeah, actually, I guess that's sort of evidence here because the 44 would also make this true, but it's looking for like the first one that's going to make it true. So just like an index of or something like that, it's generally going to find the first one that's going to make it true. All right. Okay, let's take a look at one other way of doing this. Okay, because this is getting pretty efficient, right? We've got the 5 possible values that we could be returning in this case, and I guess it's not a coincidence that there are 5 tests over here, but anyway, we've got these 5 possible values, and we're just returning whichever one ends up satisfying the problem. But here's the issue I have with this. This still isn't constant time. And when I say constant time, I'm talking about like, how does the computation time differ according to the size of the input? We saw something like this, which basically runs a loop and it counts up, right? It counts up from 1, it's calculating more factorials, more factorials, more factorials, until it finds the one that's going to be greater than or equal to n. So if n was something really big, this would take a much longer time. It would have to run more iterations of the loop. This one would take even longer. And again, we'll look into that more in more detail in just a sec. But this one over here, it looks constant because we basically just have these 5 values here, but technically it is going to depend. It is going to depend on the size of n, because if n is very small, it'll stop right here. If n is somewhat larger, it'll stop on the other side over here, right? So basically the idea here is that it still technically is going to take more time for a larger n value. And of course, like if these guaranteed constraints were a little more out there, if it was like instead of a maximum of 120, if it was like 120,000 or something like that, then that would make more of a difference, and we would find we'd have more factorial values in that case, and so it might take longer to go through the whole array. Okay, so basically, what's the solution of that? Well, here, let me make a new instance of this. So I'll paste this in, and I won't forget to put the 3 in there. There we go. Now, what I want to do is I want to make a truly constant time algorithm, something that's only going to take like a given amount of time, or like, within a certain error bound, but like something that's not going to depend on the size of the input, something where like the time it would take to calculate like an n value of 120 would be the exact same amount of time it would take to calculate an n value of 1. That's what we're looking for over here. Now, this is very close to that, but it's not quite there. So what I want to do, this is going to be kind of silly, but I'm going to make an array of 120 values, or technically more like 121 values, because I'm going to include 0, I'm going to make an array that's just going to have all the answers in it, and that's going to be it. So are we ready for that? Let's do it. So basically, let's make that array first of all. So we'll say return array.from. This is kind of a weird way of doing an array. If you guys haven't seen this before, let me know if you have any questions. This is probably one of my favorite ways of making a new array, actually. It's very weird though. So array.from, and then we have this object that just has a specified length. And then what are we going to do with this? Well, we're going to run a function that's going to take the value and the index. And what is it going to do with that? Well, it's basically going to return leastFactorial 3 at that index. Yeah, let's see what that gives us. There we go. Okay, so this basically just gave us all the results that we would get from leastFactorial 3 for any number between 0 and 120 inclusive. And I believe if I were to change this to any of the other ones, I should be getting the same results. It might take slightly longer, but I'll get the same results. Okay, now I don't want to have to recalculate this every time because that would sort of defeat the purpose. Or maybe it wouldn't. Actually, that's worth talking about. That's worth talking about. So, okay, here, I'm going to just comment that out. And I'm going to say return this at n. Let's try that. There we go. Okay, so that would work. Now, okay, actually, let me get a little more in here. Let me say const factorials is assigned the value of this large array here. I'm going to cut that, replace it with the word factorials, and paste it in over here. And it should run the same. It's the same sort of thing, right? We're saying this is this constant array, and we're just trying to find the nth value there. So why didn't I want to include this one here first? Well, mainly because it would take more time. We'd have to do calculations, right? Whereas if we have this already loaded up, well then we don't have to calculate this. All we need to do, the problem boils down to a very simple array lookup, and that's it, okay? All we're doing here is looking up a value in the array, done. So like, yeah, that's gonna be most efficient. That's gonna take the shortest amount of time, at least theoretically. We're storing this somewhat large array in memory, but I don't think that's going to be a big deal. Okay, here's the idea. This is really where I want to start talking about efficiency, time complexity, big O of n, that kind of stuff. So basically, I would say this is a big O of 1 algorithm. Okay, so big O of 1, because the time it takes is not going to depend on the size of the inputs. That's the main thing, okay? Whereas this one over here technically is kind of like, I guess this is like a big O of log n. It'd be something like that, I think. And why am I saying log n? Well, okay, I don't think it would be exactly log n because the way factorial grows, I don't think it's exactly exponential. I think it actually grows more steeply than exponential. But it's pretty close to an exponential function. You can sort of think about it as being like a multiple of an exponential function. I don't know if there's a way, if there's like a closed form formula for calculating factorials that involves like an exponential or something like that. But basically what I'm trying to say is the amount of time this is going to take, it's going to depend on n, but basically the larger n gets, the less of an impact its growth is going to have on it. So what I'm trying to say is like the computation time here. Whoa. Hey. We need to do a better job on this. Okay, that's pretty straight. There we go. Okay, so the amount of time it's going to take, like, yeah, the computation time is going to change according to the size of the inputs, but how much it's going to change is going to become less and less and less over time. So like, the difference in computation time between a value of like 1 and a value of 50 is going to be much more significant than the comparison between 50 and 100, let's say. So it's not linear. It's not like a big O of 1. It's more like, it's not like a big O of n. It's more like a big O of log n. So it's not quite as bad as a big O of n, which would be more like this. But keep in mind, we're not just looking at the time it takes to execute these functions. We're looking at how that time depends on the size of the input. So it's a math thing, it's a totally mathematical idea. I believe this one would also be something like a log n, just because, like, this is fundamentally not really that different from over here. The only real change. The only thing that we're economizing here is we've already done the calculations. We've already done the multiples, okay? So we don't need to multiply each time. We just have the values already. But the idea is that for this one, yes, it would take maybe a little more time, negligibly, but a little more time to do this multiplication every time. Whereas in this case, it's just going to bang out the values. It already has them. It doesn't need to recalculate them. So you could say, well, doesn't that mean they should be different? Like they're going to be different computation time, right? Yes, they probably would be different computation time. This one would probably take marginally a longer time, like just slightly longer than this one over here because it already has the values calculated. But this is a really important note, the time complexity is not different between these because even though this one would take more time in general, the way that time is going to scale up is not going to be different. I'm claiming that they're both log n functions. Okay, so they're both some multiple of a log function, or at least something like that. I'm using log just for the sake of simplicity. But what I'm trying to say is, if you had a log function like this versus another log function like this, these are both log functions. Even though one of them is going to take slightly longer, it's just not in the same realm of comparison as something like a linear function, because this one is just going to go up and up and up and up. Like the difference between these two is just going to keep growing and growing and growing. The difference between these two, it's going to be relatively constant. It's not going to be that different. Okay, so that's what I'm trying to say. We're talking about big O, that kind of stuff, when we're talking about time complexity. We're not talking about how long it takes. We're talking about how the computation time scales up according to the size of the inputs. Now, in this case over here, because we're doing both, because we're doing our factorial function over here, and then we're also doing this over here, I think this one is going to be more like an n log n. I could be wrong about this one, and I might as well just include the multiplication symbol in there. So actually, hold on a sec. It's going to be... Is it going to be that? Yeah, I think it will be, because the factorial function is big O of n, right? Or big O of num, I guess I should say. Because like the bigger it is, the more calculations there are going to be. Like if it's 4, there are going to be 4 calculations. If it's 10, there are going to be 10 calculations. So I would say that part is going to be n. So basically that means that this function has a much higher complexity than either of these guys. And it doesn't matter. Like, we could even do something in here where we say, like, just do another little for loop that says I value this, I goes all the way to 1,000,000, let's say I plus plus. This is obviously going to take a much longer time. Like this is going to make every repetition, every iteration of this outer for loop, it's going to make it take a much longer time, because it basically just has to count to 1,000,000 every time for no reason really, other than to slow it down. But what I'm trying to say is, even if this one has to count to 1,000,000 every time, because it only has to do that log n times, it's still considered better time complexity than this one. Now, that doesn't mean that its computation time is always going to be better than this one over here. And in fact, I want to use this opportunity to return to this over here and talk about this. Okay, so basically, if I had said const factorials is assigned the value of this thing, then we might look at that and say, whoa, that's so much less efficient now, because now we have to go through this whole thing. We have to call this other function 121 times. That's going to take way longer than just loading up the array that we already know the values of. But here's the thing, the time complexity, same. It's no different, because it doesn't depend any more on the size of the inputs than it did before. We're still calling the function 121 times, regardless of what the input is. So while the first, what I commented out here, while that might be like a constant time algorithm like this, and that's meant to be a totally horizontal line, by the way, this method over here, it might be something like this, right? So it's still constant, but it's taking a longer time each time. So, and by the way, just to be clear about what the graph is here, I'm talking about, like, on this axis, we would have n, like the size of the n, the size of our input over here, and this would be the actual, time it takes to complete the computation time. Now, just to compare that to something like our log n might grow something like this. So we might look at that and say, well, this is taking a longer time than one of our constant time algorithms, but it's actually going to execute faster than this other constant time algorithm. That does not change the fact that this one is still a constant time algorithm. Even if it's always taking a longer time than our log n function, it's still considered constant because it's not depending on the size of the input. That's the main thing, okay? So a lot of people get caught up in this idea of big O, thinking like, oh, so if it's big O of n, it must be faster than big O of n squared. Not necessarily the case. It doesn't have to do with how fast it is. It doesn't have to do with the actual time computation time. It has to do with the time complexity. It has to do with how it scales up as our inputs increase in size. So that's the idea there. Okay, so that's what I wanted to say about time complexity, big O, and all that nice stuff. As for now, we'll comment out this other one because I think I do sort of prefer this way of doing it. Okay. Rainbow asks, isn't nested loops up to n big O of n squared? Yeah, totally. I mean, usually anyway, I should say. It depends on like what's actually going on. Like this is a loop right here, right? But this loop isn't taking big O of n. It's more like log n because of the way we're checking. Like because we're trying to return as soon as k reaches a certain value, right? But if we were talking about like as soon as m reaches a certain value, then yeah, that would be a big O of n time kind of thing. And then if we were to put another loop in there, yeah, big O of n squared. Again, depending on what that loop is, right? What its conditions are. Okay, so let's just submit that. Let's make sure this is all working good. Great. Okay, so I think we're all done with that one. Nice job, everyone. Before we finish up though, I think I saw a little paste bin in here, so let me take a look at that. Okay, so Rainbow Sprinkles did it this way. Let's just put another number on this. What are we up to? 4? Okay. So what do we have here? Var k is on the value of 1, var I is on the value of 2, k is less than n. Yeah. Okay, so this is very, very similar to, I guess, was that the second? Yeah, the second one we used. So really similar idea here. Basically, the difference is that you're handling this part right in here. So yeah, I think in some ways that's probably smarter. Yeah, because I'm not really making use of the space in here, and yeah, I guess I probably should. Yeah, I like it. I think it works. It's good stuff. So that's gonna be it for today, I think.